number of students is reduced. Yeah, so just like I said, I do not take attendance, but if you like to come to the lecture, I mean, I'll try my best to make sure you understand the material. Okay. So, the second lecture, okay. Because like I will be working on other stuff like right after today's lecture, so we sometimes, okay, in the future lectures, I mean, we may, okay, talk about more than one set of slides, okay, but today I think I will just finish this one and call it a day, okay, because I have a meeting 12 o'clock, 1 o'clock, 2 o'clock, and some meetings are even overlap. So I think I'm running out of time. Okay. So anyway, back to the lecture. Before we get started, okay, one thing to announce. Okay, we usually have one homework assignment. Remember, like in the syllabus, I mean, when we went through the syllabus, we have homeworks, right? Okay, written homework. I'm not talking about programming homework. Okay, programming assignment will be given out later. Okay, but written homework, I mean, I have like I usually give out like every 2 lectures. Kind of like 2 to 3 lectures, one written homework. Okay, so sometime like around the end of this, before this weekend, I will upload written homework like to the class. Okay, so this is first thing. The second thing, okay, I forgot to mention is about APCS. Okay, I know some students are taking APCS. Previous year, okay, if the student gets like a good grade from APCS, okay, you get an extra point, okay, in the algorithm class. Okay, so I think like I tried some experiments. Like I mean, we are supposed to reward the student with like a good APCS score, right? So I mean, how do we define good APCS score? Okay, it's like this. Okay, if you answer like 4 questions right, okay, in your APCS, I mean, you can answer up to 7 questions right, of course. I mean, that's, you answer every question right. I mean, like if you answer 4 questions right, you get, okay, additional points. Yes.
You mean CPE or APCS?
APCS. Yeah.
Not CPE.
CP.
APCS is for high school students.
No, oh, see, anyway, the one for the college. Yeah. So, CP, okay, my bad, sorry. CP up to 7 questions, right? Yeah. I was talking about CP, sorry. So, if you answer 4 questions right, okay, you get 1 point. Every additional question, you get 1 additional point. Okay, toward your final grade. Okay, toward your final grade. For example, if your final grade is 85, if you answer CP 6 questions, for CP, you get 3 additional points. So your grade, final grade will become 88. Okay, I forgot to add that into the syllabus, but I just want you guys to be aware. Okay, we have this system. Okay, we have this additional grade you can earn. Okay, other than what I assign in the class. Okay, so make sure. Okay, because I think this is the graduation criteria in our department, right? We have to answer how many? 3 questions, right, in order to graduate, right? Or accumulate 3 questions, right? Right? So, because if you want to earn extra credit, that means you are doing good job, right? Doing good job, it should be better than the minimum requirement in our department. Okay, so that's why I said 4 questions. Also, I mean, from the previous experience, because I told this class 2 times previously. The first time I set the bar at 3 questions. I mean, if you answer 3 questions, you have additional point. But it turns out to be too easy. So I said to be 4 questions last year, and the results seem to be okay. So anyway, just want you to be aware of that. Okay. So let's get started on this lecture 2. Okay. Lecture 2 has 2 topics. Okay, separate topics. One is asymptotic notation. Another one is recurrence. How to solve recurrence. We actually touch each of them in the first lecture a little bit. So first is about a big O notation. Okay. We usually call this upper bound. Okay. You write Fn equal to big O C of n if there exists a constant Cn0, okay, both greater than 0, such that the following equation holds for all n greater than n0. Okay? So you can see that as long as n is sufficiently large, C times G of n will bound Fn. Okay? So that is why, we call this as upper bound. Okay? And also, be careful for this small greater or equal. There's an equal sign here. Okay, there's an equal sign here. So that's what we call big O notation. And to give you some examples, 2n squared equal to big O n cubed. I mean, n cubed obviously has a higher order than n squared, so it will be very relatively easy to find the C and n0 to make this inequality hold. Okay, you can give it a shot and take a look. So this is a very, very mathematical definition, obviously. Okay, but here, is the function that we have. Okay, and this is not a value. This both of them are actually functions. You don't treat them as values. Okay, and this equal sign is a little bit interesting. I think last week, when I talked about why you have a example on this, I told you this is notation abuse. So, I mean, because of this notation abuse, we usually only do this one way equation. So this your function is bounded by, n cube. Okay, so it's big O n cube. But you don't write the other way around. You cannot write like big O n cube equal to 2n squared. Okay, this is not the right way. Okay, but in your previous training, you may think, well, because if it's equal sign, if A equal to B, of course B equals to A, right? But okay, to be exact, the big O notation actually stands as a set. Big O of G of n is a collection of functions which satisfy this requirement. Okay, so big O G of n, so as I say, here, the left-hand side is one single function. The right-hand side conceptually actually represents a set of functions. So, that equal sign actually means 2n squared belongs to like it's an element in this set. That equal sign just means this. So that is why you cannot write it the other way around. Okay, if you write it the other way around, you cannot like say like okay, n big O n cube, which is a set, belongs to a particular element. That doesn't make sense, right? That doesn't make sense. So we have this like this is like supposed to be like what we should have should have done, should have written. Okay, but we are computer science, okay, computer science, so we are a little bit sloppy. Okay, so we just use equal sign here. Okay. But okay, because of that, okay, there are some you can say like extended version of notation abuse. Okay, so a set in a formula represents an anomalous function in the set. So, for example, sometimes we can write like this: Fn equal to n cubed plus big O n squared. So we kind of write it like this is one of the function, okay, x or put it another way. This could be some function in this set. Okay, this actually means Fn equal to n cubed plus h of n. This is a particular function, okay, that belongs to this set. But again, this is obviously a notation abuse. And again, this is one way. You don't write it the other way around. Okay? And okay. The other way, the other example like this. If you write it on the left-hand side, the right-hand side usually also, you have to also write something like this. I mean, it cannot be assigned to a function, but it could be assigned to another big O notation. So again, this represents some function. the left hand side here represents some function, and the n squared plus that some function will become an element in this set. Okay. So for any f of n in big O n, n squared plus n equal to h of n. This h of n is an element in this big O n squared. Okay, so that one is has this meaning. So the only chance for big O n appear on the left hand side is the right hand side is also big O. Okay, I mean, of course, I mean these are like examples of notation abuse. Okay, but in computer science we just try to make the discussion, easier. Okay, more like convenient, because obviously, okay, let me put it this way. If you want to be more formal, mathematical, you need to write the whole thing like here. It would be much, convenient to just write a line like this one, right? So the issues about the convenience, okay, it saves time. Okay, time is money, especially in our major. Okay, so that's why, okay, we try to simplify this terminology. Okay, but you guys just need to remember, need to understand, okay, what it really means. Okay, when we use this equal sign. Okay, sometimes when we abuse this equal sign, okay, we need to understand what it really means. So, with that in mind, okay, we also have other notation, okay, because big O represents the upper bound, right? And so it makes no sense to say your function f of n is at least big O n squared. I mean, when you say certain function is at least something, what you need is a lower bound, right? But big O can only be used to represent an upper bound for your function. If you want to represent a lower bound for your function, then we have the omega, big omega notation, okay, which represents the lower bound. I mean, it is very similar to upper bound big O, because you can see omega, big O, big omega G of n. I mean, it represents a set of functions such that, okay, you have Cn0 greater than 0, and which satisfy this inequality for all n greater than n0. And this inequality, okay, you can see now C times G of n, okay, is smaller or equal to f of n. Okay, in the big O, these two, are in position, they are different, right? So keep in mind, okay, about this. So once you change this, the positions, like in this notation, obviously, you switch from the upper bound to lower bound. So the similar notation abuse applies for the big omega notation. But, okay, we usually just write, for example, square root of n equal to big omega log n, or just abbreviate just omega log n. Okay, again, you need to pick up like C and N0, and it will be very easy to pick up C and N0 here, because log n is like a much lower in terms of order, then square root of, which is n to the power of 0.5, right? So this is log n sublinear. Okay, so you can easily pick up C of n0 to make this inequality hold. And another thing I want to remind you, okay, if n0 equals 16 works, obviously you can assign n0 to be 20, right? I mean, like this assignment, C and n0, it does not, I forgot to mention this about big O, I mean, in the big O, okay, I mean, same to a big O and in the big omega. I mean, all these C, n0 assignments, you just need to find some assignment that make this inequality hold. Okay, I mean there are plenty of assignments. Okay, that can make the case. Okay, if it satisfies this. I mean, if it is indeed like bounded or like its upper bound of or lower bound of something, then a lot of times you can easily find like a combination of C and N0. Or put it that way, there are many possibilities to find the one. You just need to find one combination. So you can see that this is, you have like this equal sign here. But you seldom, okay, other than the big O notation, we use big O notation more often. To be honest, when we discuss like a complexity, I mean, there are two notations we use more often. One is big O, one is theta. Okay, as I will mention later. These two are more commonly used. I mean, big omega, we sometimes use it, but very infrequently. So we usually don't write the big omega like this or like this. Okay, it is not like I mean, for big omega, obviously, this also represents notation of bigs, right? But because the right hand side is still a set, left hand side is still like a one element. I mean, conceptually, it just means that square root of it is an element in this set. But anyway, I just want you to understand, like when we talk about, when we use these notations, yeah, I mean, big O and use very often. And the second most frequently used one is this one, theta notation. We call it tight bound. What do we mean by tight bound? Okay, so if like the theta G of n, that means like I mean, this again, this represents a set, right? This is a set. So it is the intersection of two sets, big O G of n and the big omega G of n. Okay, so for example, 1/2 n squared minus 2n. Okay, this one equal to theta n squared. Okay, because you can, I mean, this n squared, okay, I mean, obviously, this thing satisfies big O n squared. And this thing, the same equation, satisfies big omega n squared. So because it is satisfied big O n squared, it satisfies big omega n squared. So it is, an element, to make it more formal, it is an element in theta n squared. So, I mean, you could use, give like a similar formal definition like this for theta, okay, for tight bound. So obviously you need to so you can write like okay, according to the notation here, is f of n such that okay, there exists constant, or I just C, but now we have C1 and C2. And n0 greater than 0, greater than 0, and n0 greater than 0, such that, okay, 0 smaller equal to C1 times C of n smaller equal to f of n smaller equal to C2 times T of n. Okay, for any n greater or equal to n 0. Okay, something like this. Here, I mean, I just want to point out, okay, if you resolve it back to like a forward definition here, okay, you have three constants. Not you have n0 obviously, but you have not only C, actually you have two constants, C1 and C2. And you use C1 for the lower bound and C2 for the upper bound. Obviously, this C1 and C2 are equal. You cannot have like sometimes they could be the same if the equal sign holds, obviously, right? But most of the time they are equal. Okay. Just want you to understand this. Okay, if you want to resolve it back to like a formal definition for this theta application, like a type bound. I mean, after all, type bound is the second. I would say it's the second most used notation in this class. I mean, we use theta like this type bound. I mean, to represent like the complexity of algorithm all the time. It is just we discuss. More often we use the upper bound. Okay, because remember when we discussed like the algorithm, we care about the worst case. Okay, the situation we care about. Okay, most is the worst case performance, and in the worst case performance, as long as you can bound, I mean, the worst case performance by the upper bound, then a lot of time that's good enough for our discussion. So yeah, I mean, we talk about, as I said, big O, big omega, theta, but in reality, big O used very often, theta used very often, but the omega, because as I said, like, when it comes to like time complexity, I mean, we have this, but it's not rarely used. And there are also the other two functions that gets rarely used. The first one is small o.